We are going to continue the course we started earlier in linear regression lines. The topic of today is about qualitative predictors. To remind you, we had quantitative predictors earlier where all of our variables were quantitative. For instance, y is equal to beta 0 plus beta 1 x beta 2 x2 plus epsilon. We assume that all these variables, these predictors, are quantitative before. So these are something you can measure. In linear regression lines, this part, the outcome is always quantitative. However, as we will learn today, we can have qualitative predictors, categorical predictors. So now let's relax the assumption of quantitative predictors and assume we have a choice of having qualitative or categorical variables here as well. For instance, let's focus on the data set that we have on credit line. So let me first show that to you. Here we have a balance on many other variables: age, cards, number of cards you have, the number of years of education, income, limit on the cards, and rating. These are all quantitative variables. But in the same data set, we have some variables like gender, student status, ethnicity, or marital status. All of these are qualitative variables. Gender is not a number. We cannot take an average of gender. We cannot take average of student status, for example. We cannot say the average student status is 0.5. We cannot say such things. And so thus for races, we can have many different races, but in this credit card data, we have Caucasians, African Americans, and Asian. We have three categories. We cannot take an average of these categories. So let's see how we can use that in our regression lines. So our target is to regress. Let me just put instead of y, let me write balance as a function of, let's say, age plus beta 2 income. And now we want to have somehow capture the relationship to gender, ethnicity, and so on and so forth. It turns out it's very easy to deal with quantitative variables. We can just use something called dummy variables. In order to use dummy variables, you just pick a category. So here let's focus on gender. Gender, you can have females or males. So in dummy variable version, you define an auxiliary variable. You set it to 1 whenever it belongs to one of the categories and 0 otherwise. So if my ith person is female, I set it to 1, otherwise set it to 0. Remember, you could define 1 to represent male and 0 to female, and nothing would change. So there is no problem of dealing with that. So we define an auxiliary variable, which is also called a dummy variable. Dummy variables take two values, and so if you have a category that contains only 2 values or 2 possible outcomes like female and male, then you can define one dummy variable, xi, and set it to 1 whenever it's equal to one of the variables and 0 when it's not. That way you are introducing you are just making quantitative, you can use qualitative variables in your regression lines. So for instance, so let's say balance, so let's just stick to our example in balance. Let's say balance is a function on your income income, and your gender. So G stands for gender. And let's assume we have defined gender such that it's 0 when it's male and 1 when it's female. So let's see what is our balance at a given income for males. So when it's male, the outcome is 0, so that part should be 0. So let's see what we have. When it's male, we have beta 0 plus beta 1 income. So let's see what is balance for income and females. So here, G will become 1. You have income. So let's say these are same level of income. So we have beta 0 plus beta 1 income plus B2 times G, B2 times 1, because we are dealing with female. So let's look at the differences of, let's call it balance for females and balance for males. So the difference would be this guy minus this guy, so everything will be cancelled. The only thing will be left is beta 2. And beta 2 was this. So in other words, we can say the difference, on average, the differences of balances of males and females will be beta 2. Let's say this beta 2 is $10. 10. So what we can say is that on average, the difference of males and females is $10. So females spend $10 more than males. So here, that's exactly the same regression line. So these are the coefficients you have for gender. In R, whenever you have anything in brace in quotations here, female, that means that was the part that was 1. That is the part of the outcome of your qualitative variable that is 1. So that was beta 2 in my previous example, but here in this case we only have gender here, nothing else. So beta 1 is just gender. We don't have income here, so that's the coefficient we get. First of all, this is not significant at all. So the p-value is more than 5%. It's not significant, so that is not a significant thing to say. But let's assume it was significant. If it was significant, that would mean on average females have $20 more balance on their credit card. Now that's the question of how do we deal when we have more than one qualitative variable. So let's say we have ethnicity here. If you have more than one qualitative variable, so let me just generalize it. If you have n categorical variables, then you can define n minus 1 dummy variables, and then you can consider it in your regression line. For instance, let's say, for the sake of example, let's stick to the example we had earlier. So let's say we have 3 different ethnicities: African Americans, Asians, and Caucasians. You can define it as a 1 and 0 variable. 1 if they are actually African American, 0 if not. For Asians, the same thing. So 1 if they're Asians, if not. So if you have defined your dummy variables this way, then you do not need to define any dummy variable for Caucasian, because they will become your base ethnicity. So let's say, just for the sake of example, I don't know how these numbers will look like later, but let's say the balance is regressed on AA, the dummy variable for our African Americans, and dummy variable on our Asians. And let's say, again, that doesn't mean anything. I'm just making these numbers up. So let's say beta 1 is let's say beta 1 is 20, and let's say beta 2 is negative 30. So what it means is that in comparison to Caucasians, African Americans have $20 more balance on average. And if beta 2 is negative 30, that means in comparison to Caucasians or base ethnicity, in comparison to base ethnicity, which was Caucasians, Asians have $30 on average less balance. So what on average, what is the difference of African Americans and Asians on average? I think you guessed it right, that is $50. So African Americans have $50 more balance than in comparison to Asians. So it depends how you define your base ethnicity. These numbers may change. For example, if we would have defined Asians as base ethnicity, then all these values would be positive. Why? Because everyone else have more balance on average. So here, x1i is defined as a dummy variable, which signifies that there is if you are an Asian, you get 1, otherwise 0, and if then an observation is Caucasian, you get 1, otherwise 0. So here, African Americans were treated as baseline category. So here are the results you get. For Asians, since we define xi1 as 1 for Asians, that's an indicator variable for Asians. For Asians, this one becomes 0 because they are not Caucasians. If they're Asians, they're not Caucasians. So yi is equal to beta 0 plus beta 1 because this part will become 0. For Caucasians, that's the other way around. Beta xi1 is equal to 0 because they're not Asians, but they are Caucasians. So that is beta 0 plus beta 2. And for African Americans, both of these values are 0, so the base would be beta 0. So we always need one fewer dummy variable than the number of categories we have. And this is the one that will be left alone is called the baseline. So here is the results of our regression line for the same case. We see the ethnicity category for Asians at negative $18.69. Ethnicity for Caucasians negative $12.50. Again, look at these values. They're not significant at all. But let's assume they were significant. If they were significant, we would say in comparison to African Americans, Asians tend to have $18.69 less balance on average. And for Caucasians, in comparison to African Americans, we would expect that they hold or carry $12.50 less balance. Now that's the time to work on interactions or synergy effects. So if you can remember from our earlier slides, perhaps from the earlier videos, we said that the advertising data shows that there is a strong relationship between sales and TV and radio, not that much of a strong relationship with newspapers. So that's why we decided to drop the newspaper. But let's look at some of the hypotheses we can have. For example, let's say TV ads have the highest coefficient. So if we are naive, we may say that, okay, since it has a higher coefficient, let's say if we have a budget of $100,000, let's just spend everything that we have on TV. So nothing on radio. So that's one of the options we can have. That might be right if ads on TV and radio were completely independent. But as we know that in marketing specifically, the more you're exposed to an ad, the more propensity you have to buy it. So the different means of advertisement have better effect, in fact. So usually if you hear something with 5 times, you will be exposed to that, specifically if it came from different different means. So maybe if we just so maybe the ad TVs are more effective than we have some sort of radio ads as well, and vice versa. So they're not as effective as their own. This is called the synergy effect in marketing specifically. And in the statistics, we refer to that as interaction effect. So how do we identify such effects? Just by looking at the picture, the graphs of it. One thing we can see here is that, so if we were only regressing y, which was sales, on beta 0 plus beta 1 amount of money we spend on TV plus beta 2 on radio, we would get this surface. This is a formula for a surface. This is called a surface. This is our prediction surface. And let's say these are our real values. So what we see here is that closer here and closer there, when we are on this diagonal part, what we predict is usually, which is on this surface, is usually way different from what actually happened. So here we observe more sale than what we predict, and here as well. But here in these sparse areas, we see that our prediction, which was this surface, is way above reality. So that may suggest that when we in this surface we have synergy. That means when we spend money on TV and radio simultaneously, we got better results than what we expect. When we were doing it sparsely, we get worse results. That suggests some synergy effect. The way you capture synergy effect is by adding a third term, and that third term is in terms of the product of the two values. So we want to have TV, radio, and the product of the two. We can rearrange and rewrite our regression line formula this way. For example, we can write it in TV as follows. So we just factor TV here and here. What we would be left is beta 2 radio, which is here. Beta 1 was a coefficient of TV, and beta 3 times radio would be another coefficient of that. So that means for given value of TV, if you add $1 to TV advertisement, you would expect to add your sale by beta 1 plus beta 3 times the amount you spend on radio. We can rewrite the same linear regression line this way. We can write it as beta 0 plus beta 2 plus beta 3 TV times radio plus beta 1 times TV. Again, now here, let's see how we interpret that. Let me say, for a given value of radio expenditure, if we spend $1 more, we will expect that, on average, we will expect beta 2 plus beta 3 times the amount we spend on TV effect. So, in effect, if this beta 3 is a positive value, that means the more you spend on TV, the more would be the extra value of spending on radio. So here are the coefficients we get. These are the p-values we get. They are all significant. So here it's significant at a level of 1%, which is very significant. So they suggest that there is a synergy effect, and this is a positive synergy effect. There are some things that can have negative synergy effect. That means if you want one thing to be effective, you should reduce the amount of the effect of the other part. perhaps in some of the drugs that have negative side effects that may come in place. So some of the interesting things we see here in the synergy effect is that, first of all, everything is significant. Second thing is, without having significant this synergy effect, we could only capture 89.7% of the variability. Now, once we add that synergy effect, we were able to capture up to 96.8% R squared, which is the variability of the model. The second thing is that they have a positive result. That means they are positively reinforcing each other. So let's look at some interesting results. Let's say you have spent $1,000 on TV, and you would like to, no, sorry, you have spent some money on TV, and you want to see, well, what is the effect of spending $1,000 more on TV? Here, if you can recall from our earlier result here, so we have TV as here and beta 1 plus beta 3 radio here. So let's see what's the effect of that. So it depends on beta hat 1 plus beta hat 3 times radio, times that amount. So beta hat 1 was 0.0191, beta hat 3 was 0.0011. So if we just replace the numbers inside, we would see that it is 19 plus 1.1 times radio unit. That means the more you spend on radio, the more would be the effect of this extra $1,000 that's been spent there. And that's the same thing for radio. So we're sticking to the second derivation we get, which we have it here in below. We need beta 2, which is 0.2. We need beta 3, which is 0.0011. For an extra $1,000 on TV, we will see that on radio, we will see that the effect of that in our sale is 29 plus 1.1 times the amount of money we spend on TV. So the more we spend on TV, the more effective will be that $1,000 that we spend on radio. So we have a rule in the statistical hierarchy, and that is extremely important. I want you to remember it all the time. And that says, if you have decided to keep the interaction term, you can never ever drop your values. For instance, let's say here the interaction effect was very significantly, was statistically significant, whereas radio has p-value, let's say 0.85. If that was the case, we couldn't keep this interaction effect without keeping radio. You can never ever drop this without the if you want to keep the interaction effect. That is called hierarchy rule. Because if you just drop it, it will be very, very, very hard to interpret the interaction effect the way it is. Now let's see how interaction effect works if we have one quantitative variable and one qualitative variable. So let's say we have income as one of our predictors, that is a quantitative variable. And we have another variable which is qualitative. Let's say a studentship. So studentship takes a positive value when 1, we get a value 1 when you have a student, if you get 0 when it's not. So that is the case without interaction. If it's a student, you get beta 2 here. If it's not a student, you get beta 0. So for different values of income, you see these differences. So that is without the interaction term. I'm sorry, I have to go back. Okay, there is something wrong with my laptop. Okay, good. So without interaction, that's how things will look like. If you have a qualitative and quantitative variable. So beta 2 is a coefficient if it is a student. So if you're a student, then beta 2 will be here, and you have beta 1 times income plus beta 0 plus beta 2. So that will be your new intercept. If there is no student, that will become 0. You basically have beta 0 plus beta 1 income. So that is how your regression lines would look like. And the difference of the two would be beta 2. So let's say beta 2 was positive. So that would be the regression line you get for income level for students. So sorry, that wasn't sales, that was balance. And this is the regression line you get for non-students. However, we will see that when we add interaction effects, we can get two different lines with two different slopes and two different intercepts, and that's where the beautiful thing starts. I think it's better that I spend some time on this blank case. So let's say this is balance, and you have defined a variable called student. When it's 1, let's call it S. When it's 1, that means he's a student or she's a student. If it's 0, it's not. So this is beta 0 plus beta 1 times income plus beta 2 student plus beta 3. I just put I for income, that makes our life easier. I times S. So here is also S. So balance for students would become beta 0 plus beta 1 income plus here, this is 1, we get beta 2. Here, it's 1, we get beta 3 I. Sorry, I should put I here to avoid confusion. So let's assume this is I. So if I rewrite it, what we get is just beta 0 plus beta 2 plus beta 1 plus beta 3 times I. So that's for students. Balance for non-students. Non-students will become beta 0 plus beta 1 income. Here we have 0, here we have 0, so I just don't write it. So as you can see, for students and for non-students, we get different intercepts. So this is our new intercept. So it's the intercept for students. And here is our coefficient for income. So, or better say, slope for income. So as we can see here, for students and non-students, we got two different lines because they have different. So let's say this is for students. Let's say this is for non-students. This is income, and this is balance. Let's say these vertical lines we would get for different beta 0s and beta 1s. What it means is that for lower level income, non-students tend to have more balance. For more income, that's vice versa. At this part, this amount of income, they have same balance. So as you can see, when you have interaction effects of qualitative variables and quantitative variables, things become very interesting. We get two different lines with two different slopes, and that's the beautiful thing you can get there. Here is another representation of what we said. If we didn't have any interaction effect, we would get parallel lines, and the characteristic of parallel line is that the distance of two lines is always constant along one variable. So you can see it here. If you have different income, if you have interaction effect, you get two lines with two intercepts and two slopes, and that's why you will see that at lower level income, for example, here the distance is way more than when the income is different here. The last topic in this slide, before we move into the comparison of KNN algorithms and regression lines is how to deal with nonlinear cases. So as we explained in our earlier videos, we mentioned that even if things are everything things are not looking linear, they might be linear in regression line. That means you may define a linear regression line that captures that nonlinearity. Specifically, we mentioned that such functions, although are nonlinear on their variables, they're completely linear regression lines because you can just call x2 another variable like y as z and x3 another variable like t. So they become linear, right? So here let's focus on the example we have in R, which would regress mileage per gallon on horsepower. The shape of this distribution, the shape of this scatter plot looks completely nonlinear. So to my eyes, this might be the best line that describes it. So that nonlinearity is there. So how can we capture this nonlinearity? We just introduce nonlinear terms here by keeping it linear on its coefficients. So here we could just run a simple regression line and we get what we have here. How do we know where to stop? First of all, never ever go more than polynomial degree 5. Polynomial degree 5 and above are very bad, and you should never ever use them. Second of all, you should use your test data or cross-validation to choose the best nonlinearity that will keep it. Try your best to keep it as simple as possible unless you have to go on higher degrees of polynomials. So that's my general recommendation for you. So here beta 1 was negative 0.04 and beta 2 is 0.001. You cannot explain beta 1 the same way you would explain it earlier. You cannot say for every increase in horsepower I'm expecting that the miles per gallon decreases by that much. That cannot be interpreted that way because we have another part here that is that's a function of horsepower again. Okay, so the only time you could explain beta 1 the way we did earlier as marginal effects were the times that you actually had linear terms there, linear variables. If you have nonlinear ones, you cannot explain it the same way you could do it before. So let me go to my next slide. This is another part of this lecture. And let me start with the problems that can happen when you run the linear regression line. The first one is nonlinearity. I think we explained it in detail now. Second one is dependence of error terms. That means for example, so here when you write beta 0 plus beta 1 x plus epsilon, if this is not, you assume that this is independent of y. But sometimes it's not the case. For instance, let's say you want to predict your income plus, which is equal to beta 0 plus beta 1. Let's say if you're a Harvard educated person. So if you are, it gets 1, and otherwise you get 0 plus epsilon. You may say that beta 1 suggests that fixing everything else, if you go to Harvard, you expect you earn this much more for beta 1. But that is not true, because if you were into Harvard, that means you had something called ability, which was better than others. And if that's the case, we should be able to capture that. But unfortunately, ability is not something measurable, and it's highly correlated. So that is the part you left in that error. But we know that income is highly correlated with ability as well. So something that we couldn't control is called ability. That is in our error term. It's highly correlated with income. That's why we cannot use it to interpret beta 1 anymore. That means even if the person you're studying has higher wage, maybe if he was a college dropout and would never go to Harvard, he would at that wage anyhow, because he was a more able person, it was a smarter person maybe. So that is a problem we should be very careful about when we interpret the results. The second one is non-constant variance of error terms. This case appears when you have a regression line like this, and when you look at the scatter plots of error terms, and you see that the scattered around zeros, it should be scattered around 0, but the variance of it depends on the value of x. If such a thing happens, then you cannot use your regression line the same way you do it now. You should use GLS to fix it. But again, this is not part of our discussion. I'm just going to quickly going over it. Outliers and high leverage points are something you should stay away from. You should always drop these points before dealing with regression lines. And collinearity, that means the linear relationship of your coefficients, is another point. I think we spent quite some time in our earlier videos on this part. So now the question is, when should we use linear model? When should we use KNN regression lines? In chapter 2 we learned that we can use KNN algorithms very easily, both in categorical, in making, when you have categorical outputs, when we have quantitative outputs. Now let's focus on just any quantitative outputs. To remind you, KNN algorithms, we're looking at a neighborhood, and so we do. So let me bring my. Okay, this one. Okay, so KNN algorithms for any neighborhood would look at the k-nearest neighborhoods and take the average value of the nearest neighbors as a predictor of that point. Okay, so that's what you do. You just look in a neighborhood, you choose the k-nearest neighbors, you take the values of output for these k-nearest neighbors in an n-dimensional. So here is a 2-dimensional shape, or maybe 3-dimensional. Depends how. If this is the case, this is 3-dimensional, but I cannot show you the 4-dimension. So you look at this and you use the k-nearest neighbors and take an average of them. That would be the predictions for the outcomes you have at this point. So that's the basic idea of k-nearest neighbors. I'm sure you're completely aware of that. And as you can remember, the more k's you had, so if you increase k, you have more smoother functions. So here is a schematic representation of what KNN does. Here we have k equal to 1. We have two variables, x1 and x2. We want to predict y. So if we just look at the closest observation, for this point, for example, for this very point, we look at this part. These are the closest observations to that. So for every point in that red surface, the closest observation to that will be this yellow observation. So our prediction will be exactly equal to that. For this surface, the closest observation to have is this point. So our prediction will be this point. That's why it looks like this. So do we have these steps? This highly nonlinear, very flexible function, and as you can see, it passed through all the points. For k equal to 9, you look at the 9 nearest observation, and then you draw your conclusion based on that. That's why for k with 9 nearest neighbors, you get way smoother functions like this. So the question is which one to use. We know which one to use. It depends on the shape. If you have highly nonlinear shapes, you try to use more flexible functions. If you have more linear shapes, or less flexible functions, you use more k. Here is an example. For example, you want to predict y based on x. Here is what you get based on k equal to 1. You go after all individual observations. Even though in reality we had this linear function, so let's assume this is our actual linear function plus noises, and that's why we got these points. So even with that, when you use k equal to 1, you go after individual observations. So that's a terrible thing because you went after irreducible error. Here, that's the same result you get based on k, and as you can see, it follows the line way better than this one. So depending on the shapes we have, the amount of flexibility we should use might be different. Here we have a semi linear shape. If you use a semi-linear shape, you would like to use k that is more linear, so that you have to use more k. So 1 over k should be smaller, so the best test error we get is this much. So based on k equal to 10, I think, yes, because that is 0.1. So 0.1, 1 over 0.1 is 10, so based on k equal to 10, we get this much error. If we would use a linear regression line, that would be the amount of error we would get, this dotted line. So as you can see, we outperformed linear regression lines a little bit. Here we have completely nonlinear shape. For completely nonlinear shape, we would like to use less k because that makes it more flexible. So 1 over k would be more. Again, it's slightly more. It's around 0.2. So you chose k equal to 5. So and that is the amount of error you get from your linear models. As you can see, it outperformed the linear model way more, so much better. So this is so much better than linear model because we had nonlinear shapes. But as we can see here, if we only have one variable, the KNN algorithm for prediction always outperforms your linear model. If you have 2 variables, the distance will be smaller, but it outperforms. If you have 3 variables, only in optimal levels it may outperform it for prediction. If you have 4 variables or above, no matter what KNN algorithm you use, linear model always outperform it. So a couple of lessons we learned today is that the more nonlinear your relationship, the more chance you have to get a better result if you use KNN algorithm. And the second thing is, if you have more than 3 variables, forget about KNN. Just stick to linear regression line. So these are the 2 things that I want you to remember. First one, if you have a highly nonlinear shape in low dimensions, in less than 3 variable shape, use KNN for prediction. If you want to interpret it, then forget about KNN. But if you use it for prediction, that's what you should use. Second, up to 3 variables, KNN work well. But if you have more than 3 variables, forget about KNN. Always use linear regression line. So that's about chapter 3. Thank you very much. I will talk to you in next chapter. Thank you.